Welcome to Lesson 8 Indian Space Programs. Prologue. Sputnik satellite by Russia in 1957. Then India realized and efforts started in 1960 with the establishment of Tumba Equatorial Rocket Launching Station near Trivandrum for the investigation of ionosphere. Father of Indian space program, Dr. Vikram Sarabhai initiated this program, initially carried out by the Department of Atomic Energy and then Department of Space DOS started in June 1972. ISRO and Department of Space executes space programs through Mahendragiri, Sriharikota, Trivandrum, Bangalore, Ahmedabad. India is the sixth nation in satellite technology. Video is given here. Please watch it.
Today, India is going through a communication and IT revolution. This has only been possible because of the successful Indian Space Science Program.
बहुत ही करिश्मा के साथ अपने लॉन्च पैड से जा चुका है
which was envisioned by a path-breaking visionary scientist, Dr. Vikram Sarabhai. Soon after India's independence in 1947, many leaders and visionaries from different fields emerged on the horizon. India was fortunate to have Dr. Sarabhai to take up the mantle and play a pioneering role in the field of science. Dr. Sarabhai realized that science and technology have to play an important role in India's rapid development. He said, "We do not have time, we have to leapfrog." His vision was very broad and far-reaching. He considered all aspects of Indian society. He knew that with cooperation and support from all segments, development was bound to follow. The Department of Atomic Energy was established in the year 1947. After the sad demise of its chairman, Dr. Homi Bhabha, Dr. Sarabhai was given the responsibility of chairmanship. During his tenure as chairman, Dr. Vikram Sarabhai started working on space science. The Indian space program was ushered in just a few years after the country got its freedom from British rule. Dr. Sarabhai selected a team of a few young, bright and enthusiastic scientists and started the Physical Research Laboratory PRL in one room of MG Science College at Ahmedabad in the year 1947. Later, PRL became the mother of the Department of Space. India decided to take up the space program, and a National Committee for Space Research was formed in 1962. In the natural course of events, Dr. Sarabhai headed the committee. Within 1 year, the committee decided to establish a base at Tumba to launch research rockets in order to study geomagnetism as well as natural phenomena in the atmosphere. November 21st, 1963, the first rocket named Nike Apache rushed towards its outer orbit from Tumba, marking the ceremonial commencement of the Indian space program. That day was surely among the happiest in Dr. Sarabhai's life.
It is not accidental that on the soil of India, the great space powers, the United States, the USSR and France, are collaborating with us at the equatorial range near Tumba. And even the United Nations sponsorship of this range is not merely a matter of form, but constitutes an umbrella under which, regardless of political differences, nations can collaborate in the peaceful uses of outer space.
Dr. Sarabhai was basically optimistic about the efficacy of science. His attitude found expression in his idea of taking India along the path of progress with the help of advanced science and technology. The aerial photography experiment of coconut tree disease in Kerala was enough to prove the capability of remote sensing technology and make it an intrinsic part of the Indian space science program. During the years 1969 to 1971, the formation of the Indian Space Research Organization took place. At the same time, the new SSTC at Trivandrum and the SDSC Shar Center became operational. This formed the foundation of today's fully operational spaceport of India, SDSC Shar.
In my opinion, the aspect of space research which I would like to stress most is in relation to the national capability, the self-confidence that this will generate. And if I were to give my own evaluation of this, I think the benefits of these far outweigh all the rest that we have been talking about.
Dr. Sarabhai founded the first Indian satellite communication Earth station at Ahmedabad in 1967.
Yes, we set this up because about 5 years ago we realized that this was going to be one of the most important peaceful applications of outer space and would have a profound influence on future development of communications and mass communications in this country.
Communication and mass communication,
That's
that
right.
means telephone and television.
Yes, very much so. Particularly in a country like India where the large mass of people who have to be motivated are illiterate. It is very important to, I think, have the information input as an integral part of the developmental process. And I think a powerful technique like a audiovisual presentation through television can be one of the most important motivations, a catalyst for action.
The Indian space program, born as a result of Dr. Sarabhai's vision, took shape in the early years of the space age. It took rapid strides forward under his able leadership and continued with unabated enthusiasm even after his demise. Dr. Sarabhai was responsible for providing the essential infrastructure for the Indian space program in the early years of its development, making India one of the prestigious space-conquering countries of the world. It was because he provided such a strong base that his successors could build the magnificent edifice that is today's Indian space program.
2, 1, 0, plus 1, plus 2, plus 3, 9, plus 4, plus 10 seconds, 5, plus 20 seconds.
Every member here is a part of Vikram Bhai's extended family. It is fortunate, very fortunate, that a man like Satish Dhawan, who in many ways was like Vikram, because for him it was not ego, it was not self, it was a vision of technology for national development.
He proposed that we use this new technology of mass communications for broadly educational and developmental purposes for specially directed areas of our country.
The founder of the Indian Space Research Organization, Professor Vikram Sarabhai, his focus is how space program can be used for societal development, Indian society development, particularly since we have a large number of rural areas. Maximum people live in the rural area. How this space program make an impact in the lives of our rural people. Of nearly 70% of the people live in the rural area. That was the focus.
Where we used the American satellite, ATS-6 satellite, for a period of 1 year to provide meaningful educational programs to villages, 2,400 villages in 6 clusters. In fact, many of the places didn't have TV. Even Karnataka, the first TV station was not Bangalore, it was Gulbarga, because it was one of our side programs. And this was a great hit. And when Mrs. Gandhi saw some of these programs, she was absolutely wonderstruck. Notwithstanding, at the end of the 1 year, when everybody knew that is going to be stopped, it had established the capability of satellites as an instrument of change.
Though the Indian space program started in the 1960s by launching sounding rockets, the scientists were interested in developing massive rockets that could place artificial satellites in orbit. As a result, the designing of the first satellite launch vehicle started under the guidance of Dr. Sarabhai, and he was successful in launching the design of the launch vehicle.
Very important concept that he developed in the country, that the scientific departments shall not work in silos. They work along with the user community in the country, and that is really the strength of today's ISRO. So that he laid the foundation for it, and ultimately he also realized this is also a strategic area. Once India develops the capability for satellites and he starts using it for its socio-economic development, there will be also the need for launching it. And we should have an autonomous access to the space irrespective of the geopolitical vicissitudes of the world. So he said we need to develop our own launch vehicles, and that's the SLV-3 which he promoted at that particular point of view. Today we are, for some of the best launch vehicles in the world we have, and we are self-reliant in the context of putting our own communication satellites, or even middle-level communication satellites, and also our remote sensing satellites. So these are all the product of a vision where he knew that the space can play a crucial role, provided we know how to use it and how to create an institutional mechanism in the country to use the space as a tool, innovative tool for development.
India launched its Rohini spacecraft successfully with its own launch vehicle SLV-3 on July 18, 1980, and joined the elite club of nations with satellite launching capabilities. On May 20, 1992, the first augmented satellite launch vehicle carried the 106 kg satellite SRAS-C and placed it in the near-Earth orbit. The proven workhorse of ISRO is a 44-meter high rocket, the PSLV. PSLV has a glorious history of 18 consecutive successful flights. The first flight of the geostationary satellite launch vehicle took off successfully on April 18, 2001. Since then, it has launched satellites, GSAT-1 satellite, GSAT-2, EduSat, and finally INSAT-4CR. Between 1975 and 2011, a total of 55 Indian satellites were orbited by ISRO.
India has 500,000 villages, and if we want to really create the counter forces to urbanization, which everybody agrees has its own great problems, if we want to see that some of our best people continue and can have a meaningful, qualitatively rich experience, even if they are in villages, then we can use these new techniques to bridge that information gap, that contact with the wider sphere in the world.
A successful project in the field of rural development was carried out in the Kheda district of Gujarat between the years 1979 to 1990. It was repeated during the period 1996 to 2002 in the Jhabua district of Madhya Pradesh. Both these communication projects made a great positive impact on the rural population.
Most unique applications are in the areas of telemedicine and tele-education. You know that number of our people in remote areas and villages, they are illiterate. How the classrooms can be taken to the villages has been demonstrated through the tele-education program, and this is world's unique program. No other country has got such a program.
Here let us see some of the Indian satellites. Aryabhata, which is the first satellite in 1975, April 19th. Second one is Bhaskara 1. Then Rohini, Apple 1, communication satellite put in geostationary orbit. Then Bhaskara 2, INSAT 1A, 1B, 1C, 1D, 2A, 2B, 2C, 2D, 3A, 3B, 3C, 3D, 3E. It is joint venture of DOS and DOT, Indian Meteorological Department, All India Radio and Doordarshan. Source A, B, C, D. IRS 1A, 1B, 1C, 1D, P2, P3, P4, P5, P6. MESOT 1, that means Kalpana 1, meteorological satellite, GSAT 1, GSAT 2. These are some of the Indian satellites which was our nation. Rockets. Rocket is nothing but launching vehicle. SLV 3, it is first experimental satellite launch vehicle. It was a 22 meter long, 4 stage, 17 tons used solid propellant. Second one is ASLV 5 stage solid propellant vehicle, 40 tons and 23.8 meter long. Third one is PSLV, which is 4 stage solid and liquid propellant system alternately, 44.4 meter tall and 294 tons. Fourth one is GSLV, which is 49 meter tall, 3 stage, 414 tons, capable of placing satellite of 1800 kilogram. Next one is India's first mission to moon. ISRO sent unmanned spacecraft to moon named Chandrayaan-1, which project director Mailsamy Annadurai, he belongs to Coimbatore only. And also Mangalyaan to Mars, which also recently successfully sent to Mars. And Chandrayaan-2 also in plan. Video is given here. Please watch it.
It's from here, the island of Sriharikota near Madras, nowadays called Chennai, in the Bay of Bengal, that India launches its satellites using its own launchers. At the Vehicle Assembly Building, the Indian PSLV is almost ready and awaits its passenger for what is an important first for India, a mission to the moon. Here is Chandrayaan, the Indian lunar craft under preparation in Bangalore. Chandrayaan means journey to the moon in Hindi. India has already built and launched many satellites, but this is the first time that it will venture beyond Earth's orbit.
Chandrayaan is a very major milestone as far as the Indian space program is concerned. It has been the dream of the Indian scientists to send a satellite around moon and then collect more data about the surface features, minerals and so on. That dream is going to come true through this mission, which is expected to take off shortly.
To ensure a successful lunar mission, India has had to show expertise in various fields. Indian engineers have put in place everything needed to send a spacecraft around the moon and develop the technology to study the Earth's natural satellite. For India, Chandrayaan represents a scientific and technological challenge.
The challenge is basically we are sending the satellite from here to 400,000 kilometers away. So it's quite far off. So we have to make sure our trajectory is correct and the angle or the orientation is correct and the timing is correct. When we reach the moon, moon must be at the exact place as we designed. So we make sure our guidance and control, with the propulsion system, with the communication system, everything is in place perfectly.
On its own, the Chandrayaan spacecraft is not enough. An entire ground network is needed to monitor and control it. sending commands and receiving data. So, about 30 kilometers outside Bangalore, the Indian Space Agency has built a tracking station which includes a 32-meter antenna, the heart of India's future deep space network. This antenna, linked with a number of other centers, will pick up measurements from various instruments on board Chandrayaan, enabling the scientific community to study the moon remotely. It's a technological feat, but Chandrayaan will also differ from earlier lunar missions in offering complete lunar mapping.
We are going to look at the moon slightly differently than the people have looked at, are looking at. That is, we have looking at the moon very, very systematically. Take the whole moon, systematically take the whole moon's pictures, both for the mapping, chemical mapping, mineral mapping is concerned. We want to make a repository of the whole moon, what moon contains.
One of the important aspects of Chandrayaan is its international character. Of the 10 or so research instruments on board, 6 are the result of cooperative efforts, including 3 with the European Space Agency. For Europe, this is an extra opportunity to go into space, as missions are rare. In addition, the 2-year flight around the moon should provide new data to complement that gained on previous missions.
Apollo has been a very long time ago, and instrumentation has really significantly changed since then. Another important feature of the Chandrayaan mission is that it goes very close to the moon. It goes to a circular orbit of 100 kilometers, which allows imaging of very detailed nature. The Apollo missions, yes, they went down to the surface, but only in a limited number of spots, whereas Chandrayaan tries to do detailed imaging of the entire sphere of the moon.
For the European Space Agency, Chandrayaan also represents an opportunity to reuse improved versions of the instruments that studied the moon on its SMART 1 mission. It's also a chance to send new instruments that will be used in upcoming ESA missions, such as the Bepi Colombo mission to Mercury. With this lunar mission, India is sending out a clear message about its independence and its ambitions.
PSLV-XL will inject Chandrayaan-1 into an elliptical transfer orbit, ETO. ETO, measuring 250 kilometers perigee and 22,000 kilometers apogee. PSLV will inject the Chandrayaan into this orbit at a velocity of 9.89 kilometers per second. From here on, all the post-launch operations will be coordinated by ISRO Telemetry, Tracking and Command Network, ISTRAC, Bangalore. The existing network of ISTRAC ground stations, along with support from foreign agencies, will track and communicate with Chandrayaan-1 during its journey towards the moon. The orbital period of the spacecraft in ETO-1 is 6.5 hours. The spacecraft circles the Earth for 3 to 4 times in the same orbit. The LAM is fired near perigee, which increases the apogee to 40,000 kilometers and enables Chandrayaan-1 to go into the second extended transfer orbit, ETO-2. The orbital period of the spacecraft increases to 18 hours. After the second LAM firing, Chandrayaan-1 will go to the third extended transfer orbit, ETO-3, increasing the apogee to 70,000 kilometers. The orbital period will be 24 hours. Chandrayaan-1 will be put into an elliptical orbit where the apogee will match with the distance of Moon from Earth. Satellite will take 11 days to complete one revolution in this orbit. During subsequent revolution, the trajectory correction for approach to Moon will be carried out. Beyond the 100,000 kilometers, the ground stations of the Deep Space Network will provide support to the mission. From here, the spacecraft will coast along for about 5.5 days before it reaches the vicinity of the Moon. The newly established Indian Deep Space Network, having 18 and 32 meter antennae at Bailalu, near Bangalore, is a very unique facility, having several critical technologies established for the first time in the country. The 32-meter antenna and the associated electronic equipment has been designed and developed for ISRO by Electronic Corporation of India Limited, ECIL. ISRO Satellite Center supplied the feed subsystem. On-site installation and commissioning are executed by ISRO Telemetry and Tracking Command Center, ISTRAC. Operating in S and X bands, the 32-meter antenna is capable of receiving extremely weak signals from the spacecraft, which are millions of kilometers away from Earth in deep space, and can also send very strong signals to the spacecraft. An 18-meter diameter antenna working in S and X bands will also support the mission. The Indian Deep Space Network antennae can be operated remotely from ISTRAC Network Control Center at Bangalore through a monitoring and control system. As Chandrayaan-1 spacecraft travels into deep space, mid-course corrections will be carried out as and when required. When the spacecraft is about 500 kilometers from the lunar surface, a major maneuver called Lunar Orbit Insertion, LOI, is performed. Chandrayaan-1 will achieve its final moon orbit 20 days after the launch. After this, Chandrayaan-1 will enter into an elliptical orbit around the Moon, with the nearest point being about 500 kilometers from the lunar surface, and farthest point being about 5,000 kilometers. After the subsequent health checks, the spacecraft's orbital height is planned to be lowered through a series of planned maneuvers to achieve the target altitude of 100-kilometer circular polar orbit over the surface of the Moon.
After reaching operational polar orbit, the payloads will be commissioned one by one. The first to be commissioned is the Moon Impact Probe, MIP, a technology demonstrator. It will be released at the earliest opportunity once operational orbit has been reached.
After its release from the spacecraft, the retro rocket of MIP will be fired, and it will slowly start its descent to the lunar surface. During the descent, MIP's video imaging system will acquire images of the surface of the Moon. The mass spectrometer will measure the constituents of thin lunar atmosphere, and the radar altimeter will provide instantaneous altitude and hence give inputs for future Indian soft landing missions. Thereafter, MIP will impact on an identified area in the south polar region of Moon.
The payloads on Chandrayaan-1 are engineered to acquire scientific information on the Moon through remote sensing in the visible, near-infrared, microwave, low and high-energy X-ray regions of the electromagnetic spectrum. The celenological mapping will identify different features on the surface of the Moon and will help us understand the different layers of the Moon's crust. TMC and LLRI will carry out topographic mapping of the lunar surface.
TMC will take three-dimensional black and white imagery of the lunar surface with a resolution of about 5 meters. LLRI will provide accurate altitude or height information of the spacecraft above the lunar surface for topography and gravity mapping.
The chemical mapping of the lunar surface will help us in understanding the formation and evolution of the moon, as well as in finding out the possibility of lunar mining for precious elements. 6 and HEX will carry this out.
6 will measure fluorescent X-rays coming from the moon from lighter elements like magnesium, aluminium, silicon, calcium, and iron. On the other hand, HEX will map the heavier radioactive elements like uranium, thorium, and lead.
High-resolution maps revealing mineral composition will help us in understanding the early evolution of the moon, provide information on lunar resources, and support the planning of future missions. HiSci, SIR-2, and M3 will provide these maps.
HiSci will rely on the visible and near-infrared rays reflected from the moon and will slice the incoming light into 64 parts to observe many specific details. SIR-2 will help to analyze lunar surface and to study the vertical distribution of lunar crustal material. Besides, it investigates the process of basin, maria, and crater formation on the moon, and it will survey moon's mineral resources. Similarly, M3 will explore lunar mineral composition in the context of moon's evolution.
Radon will measure the nature and composition of the radiation in the vicinity of the moon. This data will help us in assessing the radiation shielding requirements for future human missions.
Radon will qualitatively and quantitatively measure the particle flux, deposited energy spectrum, accumulated absorbed dose rates in lunar orbit.
SARA will be the first ever energetic neutral atom imaging mass spectrometer to be used for planetary.
Next one is weightlessness. Floating in satellites orbiting the Earth, not as zero gravity condition, feeling of weight on the ground. Astronaut is in satellite, both have the same acceleration towards Earth, so astronaut doesn't exert any force, so there is no reaction. That's why astronaut feeling of weightlessness. Video is given here. Please watch it.
Now we'll discuss a term called weightlessness. What do you mean by weightlessness? When I talk of weightlessness, I mean it is the condition that exists for a body when there is no force of support on the body. That means it is a condition in which the body does not feel its weight at all. I'll give you some practical scenarios when we can feel the weight of a body. For example, even if you are not doing anything, you are simply standing on the ground, you can feel the weight of your body, right? But there are certain conditions when you do not feel the weight at all. For example, during a free fall from a, say, 2-story building, if you are falling down, or if any of you have ever tried bungee jumping, during that period, you will not feel your weight. You will feel as if you don't have any weight at all. So that condition is known as weightlessness. When there is no force of support on the body, you don't have any force around you which is supporting you. You are under a condition of free fall. Here you can see in this case, the apple, when it falls down the tree, when it is falling down towards the ground, this is a state of free fall. So it is under a state of weightlessness, right? Now we will relate this term. So any free fall of an object is an example of weightlessness. Now we will relate weightlessness to the orbital motion of satellites. How is weightlessness related to the motion of the satellites? Now in case of a satellite, let us suppose this is the Earth and this is a satellite which is rotating around the Earth. So what happens in this case? There is one acceleration, there is an acceleration which acts towards the center of the Earth, right? What is that acceleration? There is one acceleration which is called centripetal acceleration, which is acting towards the center of the Earth, right? At the same time, there is one acceleration which is Earth's acceleration due to gravity, which is balancing this centripetal acceleration. That means these two accelerations are equal in magnitude and they are balancing each other. So if you consider of a situation inside the satellite, so inside the satellite everything is in a state of free fall because there is no acceleration at all. So when there is no acceleration at all, that means whatever movement is taking place is under uniform velocity. Therefore you can say that inside a satellite weightlessness is experienced. So inside an orbiting satellite, weightlessness is experienced. Weightlessness is experienced. Why? Because there is one acceleration, that is centripetal acceleration towards the center of the Earth. At the same time, there is Earth's acceleration due to gravity, which is outward from the center of the Earth. And these two being equal and opposite cancel out each other. So inside the satellite, everything is in a state of free fall. Now that we have discussed almost all the topics related to gravitation, while before ending the chapter, we will look at 1 or 2 numericals just to get a feel of the entire chapter.
Then points to remember. Here some of the points were given, so you can go through it carefully for your future knowledge. In the evaluation part, some of the questions were given. You can answer it carefully. Thank you.